Hello everyone. We are in the latter part of chapter 1. Now we know that molecules can have a whole number charge on its atoms. That charge is called a formal charge. It can be negative or positive. But molecules in general can have a partial electric charge on their atoms, partial positive and partial negative charge. So let's explore that idea a little more deeply. Now let's do this. Let's start with two chlorine atoms. I just realized that this is going to look like something we've done before, and well, it's similar but not exactly the same, showing how two chlorine atoms brought together will form a covalent bond. The two chlorines starting out will be electrically neutral. The number of electrons equals the number of protons. There are in each chlorine atom 7 electrons in that outer valence shell. So the two chlorine atoms get close enough together, their valence shells overlap, and they share a pair of electrons. There's a covalent bond formed between them. Now this is now a molecule. It's a Cl2 molecule, and it turns out this is the way that naturally occurring chlorine gas exists. Chlorine, one of the elements, if you examine a chlorine gas, you don't find individual atoms, you find these Cl2 so-called diatomic molecules. Now both chlorine atoms start out electrically neutral. When they brought together and they bond, the electron pair is shared evenly between them. It lies right smack in the middle. It's not shifted towards one or the other. It means that both chlorines in the molecule maintain their electrical neutrality. They have no charge on them. All right, let's make a different molecule where the elements are different. We're going to bring a hydrogen atom to a chlorine atom and form a bond. This is, of course, the chlorine atom with its 7 valence electrons, and hydrogen with its 1 electron, which is its valence electron. They get close enough together, valence shells overlap, and they share the electron pair, one coming from one from the other. All right, and we have an HCl molecule. Now, both hydrogen and chlorine atoms are electrically neutral. When they bond together like this, though, we find that, well, they're not going to be electrically neutral. Both atoms actually exert a pull on that shared pair, and one pulls more strongly than the other. It's like a tug of war between the hydrogen and the chlorine. In this case, it turns out that chlorine pulls more strongly on the shared pair. The shared pair shifts away from the hydrogen towards the chlorine. The effect is to give the chlorine atom an excess of electrons, conferring on it a negative charge. The hydrogen now left with a deficiency of electrons. It has a positive charge. Now this is not a -1 and a +1. It's a fractional charge, and we introduced the symbol delta, small case delta, which means fractional or partial charge. Today we know what the charge is. It's been measured. I believe it's in an HCl molecule. The negative charge is -0.18 and hydrogen +0.18. Well, here we say the sharing of the electron pair is uneven. The chlorine has a greater share of the electron pair than the hydrogen. As a result, this covalent bond has a negative end at the chlorine and a positive end at the hydrogen. We refer to that as a polar covalent bond. Moreover, the molecule HCl itself, one end is negative, the other end positive. We say that the molecule as a whole is a polar molecule. And that's what this area of study is about, is that molecules can have an overall polarity where there's an uneven distribution of charge, one end negative, the other end positive. Other molecules will have a symmetrical and even distribution of charge. One molecule polar and the other nonpolar. All right. Now, the HCl bond is called a polar bond. Back to the chlorine, because there isn't a because there's an even sharing of electron pair. There's no development of charge, and we refer to that as a non-polar bond. No charge development is called a non-polar bond. All right. Now, mention that the chlorine and the hydrogen atoms, when they're bonded together, there's a tug of war that ensues, each atom pulling on that shared electron pair. Chlorine wins the tug of war. That intrinsic attraction that atoms have for the bonding electrons is called electronegativity. Electronegativity. And this has been studied over the years. The famous American chemist Linus Pauling was the first to develop a way of quantifying this electronegativity. We don't go through the details of how he did that in his measurements, but he came up with a scale of electronegativity values. The scale runs from 0.7, the lowest, to 4.0, the highest. The element, though the higher the value, the higher the electronegativity. Electronegativity means the intrinsic attraction that an atom has for its bonding electrons. So the chlorine versus hydrogen, the chlorine, as we saw, pulls more strongly. It has a higher electronegativity than the hydrogen. And Pauling is one that figured out a numerical rating for all elements. The element with the highest electronegativity is fluorine, and it's assigned the value 4.0. And the one that's the lowest is the element that lies on a diagonal, where fluorine's at the upper right, and the element that's at the lower left, I believe, is francium. I think francium, the group 1 metal, is the lowest. Now, we talked about the HCl molecule being a polar molecule. Polarity itself actually depends on two factors. First, it depends on the magnitude of the positive and negative charges. For the bond polarity, this largely depends on the difference in the electronegativity of the bonded atoms. So the larger the difference, the greater the charge magnitude. But as well, there's another factor here. It depends on how far apart the positive and negative charges are. The farther apart they are, the greater the polarity. Now, if you're talking about bond polarity, this will correspond to the bond length. Some bond lengths are shorter, some are longer than others. And if you have a polar bond, the longer the bond, that's a factor contributing to a greater polarity. So that these two factors that come into play in overall polarity, the actual overall magnitude polarity can be shown to be the product of these two factors, the product of the charge and the distance between them. It's the charge times the distance. And this quantity is called a dipole moment, and it's given the symbol mu. So mu is defined as the charge magnitude times the distance between the charges. Technically speaking, mu is a vector quantity. Now, if you recall from physical science and physics, a vector quantity has two aspects to it. It has a value or magnitude, and it has a direction. Now, some quantities, just have a value but no direction, like mass. The idea of direction is just not related to it. It's called a scalar quantity. So if the quantity has just a value, it's called a scalar. If the quantity has both a value and a direction, that's called a vector. One of the most common examples of a vector is a force, and if you study physics, you learn about force vectors. You spend a lot of time on that. The dipole moment is actually a vector, and we'll understand this as we proceed in our study. Now, chemists have done lots of measurements and calculations. Measuring and calculating these dipole moments, they have to decide on units. The standard unit for charge is the coulomb, capital C, and the standard unit for distance is a meter. So the dipole moment taking charge times distance, that unit comes out to a coulomb meter. Now, looking at measured and calculated mu values for molecules, you find that their average is about 3.3 times 10 to the minus 30 coulomb meters. The value itself, wouldn't have any meaning, but just note that value. Taking that as the average, what Peter Debye did, the famous physical chemist, proposed that a new unit for measuring dipole moment be created, and it's called the Debye, and it's abbreviated capital D. 1 Debye is 3.36 times 10 to the minus 30. It's the average measured dipole moment value for molecules. Now, things can be lower or higher than that. All right. Now, I referred to electronegativity and the Pauling scale. It turns out that there's a systematic variation in values of electronegativity for elements. Now, I'll remind you that the value is not measured directly. It's actually based on experimentally measured values. Calculations are done, and it's placed in a framework of an actual scale, as I say, from 0.7 to 4. But these are values for the representative elements, and the ones in the middle are left out. If you look at how they change going across the row, down a column, I think you can discover the systematic variation there. All right, now there's a few, maybe some discrepancies along the way, but going from left to right, electronegativity increases across any row. Going from bottom to top, electronegativity also increases. And one way to remember that trend, now if I had a task, if I'm a student in a course and I learn the trend, and I'm going to say to myself, okay, I got to remember the increase to the left, increase from bottom to top, and in a day I'd get it mixed up. So one way to not get mixed up, if you remember the single factoid, that fluorine in the upper right hand corner of the periodic table is the highest, it's 4. If you can just remember that little factoid, fluorine is the highest at 4. That if it's the highest, then everything to the left that would be lower. That logically implies that values increase from left to right. Fluorine being the highest, everything below it is lower, so that implies that values increase from bottom to top. Now, mentioned here that for a single bond, one of the biggest contributing factors is the difference in electronegativity. So if you have here, okay, let's say a silicon phosphorus bond, the difference in electronegativity reflecting the difference in charge magnitude, that comes out to 0.3 units, as let's say opposed to aluminum chlorine bond, 3.2 minus 1.6, that's a 1.6. So 1.6 is a bigger difference, so there'd be a bigger charge development in an aluminum chlorine bond versus a silicon phosphorus bond. That's one kind of application of electronegativities. All right. Now, I mentioned that dipole moment is really a vector quantity. And we have molecules that have an overall polarity or dipole moment. And chemists have developed a kind of graphical way to show and represent that overall polarity, that dipole moment, and it uses the famous classical dipole moment arrow. It's an arrow with a short vertical line segment at the tail end. So now a simple example, HCl. We already know that that has a polar bond, a polar molecule. the chlorine end is negative, the hydrogen is positive. So the dipole moment, we draw the arrow, the tail at the hydrogen, head of the arrow at the chlorine. That's the meaning of the dipole moment arrow. The head of the arrow points to the negative charge and the tail end to the positive charge. Head to the negative charge, tail to the positive charge. So if in a graphical way to illustrate the dipole moment, the polarity of HCl is to draw this little arrow like that. The length of that arrow has meaning as well. That would reflect the magnitude of the dipole moment. So if we had a bond with a relatively small dipole moment, you draw a little short arrow. If you had a relatively big dipole moment, you draw a longer arrow. All right. Now, so far the discussion has been with respect to diatomic molecules, the polar bond and the polar molecule. But what about molecules that are larger, that have 3 or more atoms? Now, indeed, they may or may not have an overall polarity. A molecule with a polarity has a negative, positive end, and the opposite end negative. One end is negative, the opposite end is positive. And there's 2 basic ways to assess that. And I'll show you the first way. Let's take water as an example. And think of this as an analysis. Our task is to determine, does the water molecule have an overall polarity? So the steps to that process are as follows. Step 1 is draw the structural formula. That's something we talked about earlier on. Then you have to write the 3D formula for it. And that's something we also discussed. So I'm writing the 3D formula for a water molecule. Why do I get this? Just a quick review. There's 4 sets of electrons, 2 bonds, 2 lone pairs. Those 4 sets splayed out would be at a tetrahedral orientation. If you look at the hydrogens themselves, they're angled like that. You know, they're not linear. So the H2O molecule, now that's its basic shape. Interestingly, the technical term for that shape, don't laugh, it's called the bent shape. But anyway, now what we next do is look at each of the individual bonds and assess the polarity of that. And that's now going to be based on the difference in electronegativity. Well, let's see. We need to go to the electronegativity table here. Hydrogen 2.2, oxygen 3.5. Oxygen clearly higher than hydrogen. So the hydrogen end would be positive, the oxygen end of the bond is negative, and a delta plus on the hydrogen, delta minus on the oxygen. Again, these are fractional charges, they're not full unit charges. But both hydrogens have the designation of their partial charges that we find here, the oxygen with partial negative and the hydrogen partial positive. All right, now this general principle, if you have a molecule with several atoms, let's say some of the atoms are positively charged, those all act like individual point charges. Let's say, for example, positive charge, all those positive point charges. They're going to act like a single positive charge that's concentrated at a point in the center of those individual charges. So such that the sum of all of the charges of the individual points equals the total charge at that center point. That's called the center of charge. If it's positive charge, you say center of positive charge. If it's a negative charge, you say center of negative charge. So what we next do in this is to figure out the center of positive charge for the water and the center of negative charge. Now, the positive charge in the molecule is there's two places where we find positive charges at each hydrogen. The center of the positive charge is on a line joining the hydrogens and halfway between the hydrogens. That's where the positive charges of the hydrogens are going to act like they're concentrated. Right? That's that point there is the center of positive charge. Now, the negative charge is only in one atom, so the center of negative charge is obviously in the middle, in the center of the oxygen. Here's a general rule. Once you figured out the center of negative charge, center of positive charge, if they're in separate points in space, the overall molecule has a polarity. If the center of negative and positive charge are in different locations, that molecule has an overall polarity. And so water obviously has an overall polarity. We could say water is a polar molecule. All right. Let's look at another example. We showed previously that when you have this Cl2 molecule, there's both chlorines are electrically neutral, and that's a nonpolar bond and a nonpolar molecule. But for a molecule to be nonpolar, does that mean that all of its atoms are uncharged? You think about that. Well, the answer, interestingly, is no, and we see an example of that right here. Boron trifluoride. This is the 3D formula for it. I'll quickly go over how we get that, and then just before I do here, one point about the kind of analysis we're doing. Our challenge here is to determine if a molecule has an overall polarity or not. And you have to do really two things. You have to have the correct geometry, and you have to be able to assess the polarity of the individual bonds. You have to have the correct, first of all, you have to have the correct structure formula, then you have to have the correct 3D formula, and you have to know, where the positive and negative charges are. Now, BF3 molecule, there's a central boron. If we did the structural formula, 3 fluorines singly bonded. If we apply the valence shell electron pair repulsion rule, there are 3 bonds, no lone pairs, the 3 sets of electrons splayed out at maximum separation. That's a planar triangular geometry, 120-degree bond angle. Now, to figure out the charge polarity, we need to look at figure out the charges by the electronegativity difference. Now, we can go to the electronegativity table as we did before, but if we have a periodic table, boron and fluorine lie in the same table. Now let's go back to the electronegativity. There's boron and there's fluorine. That's really what I show. I'm not looking at the values. Don't look at the values, just look at their location. They're in row 2, and they're in the same row. And remember, the trend is that electronegativity increases from left to right. Boron is further to the left than fluorine. Fluorine has a higher electronegativity than boron. So each BF bond has a polarity. Each fluorine has a partial negative charge. The boron is partial positive charge. Now, the last step in this approach is to figure out where the center of negative charges are and center of positive charge. Well, the easiest for the center of positive charge, there's just one atom that's positive, so the center of positive charge is in the center of the boron. Now, the 3 fluorines, they're all alike. They all be equal in charge, and they're highly symmetrically arranged. What would be the center of their negative charge? Can you see? Well, it would be smack in the middle of the boron. All right, and smack in the middle of boron, I haven't shown it in the diagram here, but there's a partial negative charge. You see the centers of positive and negative charges are located at the same point. And when that occurs, there's no overall polarity to the molecule. It has a net polarity of 0. All right, now the alternative way of evaluating molecular polarity, using the concept of dipole moment. Here is what you do. You'll have to figure out the 3D formula for it. Based on electronegativity values, you figure out the charge polarity, just as we did before. But instead of looking for centers of negative and positive charge, you do this. And let's illustrate it with this example here. This is called dichloromethane. All right, here's the 3D formula. Now, let me just mention here, that's something that we're just learning about. In this 3D formula, it's called a wedge 3D formula. We position the molecule so that the CCl bonds here and here are in the plane of the drawing. Hydrogen here would point away, so we use a dashed line for that. This other hydrogen points toward you, the viewer use a bold line. All right. Now, the carbon-chlorine bond. Now, chlorine and carbon in different parts of the table are not in the same row or column, so we've got to use electronegativities there, so we'll go back to electronegativity. Chlorine is 3.2, carbon is 2.5. Chlorine is larger, therefore the chlorine would be the negative end and the carbon positive. Now, I'm not putting in the delta symbols. Instead, I'm drawing the dipole moment arrow vector. So that the head of the dipole moment arrow is toward the negative atom, that's the chlorine, and the tail end is towards the positive end, that's the carbon. And so both the CCl bond have bond dipole moments indicated in green. That's just an arrow running right along the bond with the head of the arrow towards the chlorine. Now I've got the carbon-hydrogen bonds here. They don't have the same electronegativity, but in fact, let's go to the table and look at them. Carbon's 2.5, hydrogen's 2.2. The difference in them is such that the hydrogen, being a lower electronegativity, would be the positive end of that bond dipole, and the carbon would be the negative end. All right. Whoops. There we go. There's a rule, though, and the let's see, we're at the bottom right here, at the bottom of our slide, print where it's asterisk. If the difference in electronegativity values between two bonded atoms is 0.3 or less, the resulting bond dipole moment will be small and can be ignored. That's just kind of a working value to simplify things. When we figure out polarities and using dipole moments and bond dipole moments and things, we're doing that qualitatively. We're not doing it quantitatively, rigorously. So this is just kind of a rule of thumb. If there's a small difference between electronegativity and it's small enough, we can ignore that polarity. Since carbon and hydrogen, their difference is 0.3, they fall within that standard. So we don't have to sketch in the bond dipole moments for C and H. We just ignore it. And that simplifies the analysis greatly. So the next thing is to get the net dipole moment for the molecule. In this case, it's the resultant of the two carbon-chlorine dipole moments. It's the net effect of the two CCl dipole moments. All right. Well, I think you can intuitively see that the resultant, the combination of those two, would be a single dipole moment arrow, which basically bisects the CL-C-Cl angle here. All right, directed in this direction shown in the red. All right, and now that's sufficient for figuring out the dipole moment of the molecule. We're not doing it rigorously quantitatively. If this is a physics class, we would indeed do that. Just a quick mention on that for those who are physics savvy. When you figure out the net vector, that's called vector addition. You take the two; these are vectors of dipole moments. You construct a parallelogram. So you draw a line like this, and the net dipole moment is the diagonal of that parallelogram, and that length would be the true length of the vector there. So, well, and this, as I say, this is would have been qualitative. So that's good enough. We can see that this molecule has a net polarity. It therefore is a polar molecule. The dipole moment mu would be greater than 0. We're not calculating Nash-Divide, just noting that it's greater than 0. All right, and let's do some other examples. Let's move to the one on the right. This is carbon tetrachloride. This is the correct 3D formula. And now the carbon-chlorine bond we know already is a polar bond. The dipole moment arrow is sketched in, head of the arrow towards each of the chlorines. All right. Now we ask, what's the resultant of those 4 carbon-chlorine dipole moment components? What's the combined effect of all those? Well, I appeal to your kind of intuitive sense here. We're not being rigorous. It's highly symmetrical. There is no single, a couple of more towards one direction than the others. They really balance each other out. They cancel each other out. So the combined effect of all these individual carbon-chlorine dipole moments is zero, and so the dipole overall for the molecule is zero. It's a non-polar molecule, and this is ironic. Even though there are partial charges on the chlorines, partial charges on the positive, because of the highly symmetrical arrangement of the negative charges on the chlorine, the net summation, the net resultant of all those individual bond dipole moments is zero. All right, this is a nonpolar molecule, even though it has polar bonds. Interesting irony there. All right, now I move to the center molecule. Again, to evaluate the overall polarity for a molecule, you have to have its correct 3D formula, and you have to have information on the differences in electronegativity to give you the charges. This is the ammonia molecule. This is something we talked about before. Here is its 3D formula. Overall, you'd say a kind of a tetrahedral array. The corners of the tetrahedron, one corner is a lone pair, the other corners are the hydrogens. All right. And the 3D formula is the wedge drawing, position such that the NH bond's in the plane of the drawing, the N lone pair is also in the plane of the drawing. This hydrogen is bold, this hydrogen is dashed. So this hydrogen points toward you, the other one points away. All right, now we have to look at the individual bond NH. You're going to go to the electronegativity table. So nitrogen's 3, hydrogen's 2.2, nitrogen's a bigger value. So we sketch in the bond dipole moment. Nitrogen being one negative in the hydrogen, the head of the arrow points to the nitrogen, the tail on the hydrogen. So we sketch the bond dipole moment along each NH bond like so, so that the head of the arrows all point to the nitrogen. Now the lone pair, well, we really can't ignore it. If you're nitrogen and you were blind, you would feel a large negative charge right up here. It's as if you're attached to a highly electronegative atom. And so the lone pair being a high degree of negative charge, it acts like a highly electronegative atom, and there's an actual dipole moment component created there. It's called a lone pair dipole moment. And it's generally always the head of the arrow towards the lone pair, and I've sketched that in. That blue arrow pointing vertically is the lone pair dipole moment. Now, the three NH dipoles, what we need is their resultant, the combined effect of those. And we'll kind of appeal to our intuition again. The combined effect of those, because they're highly symmetrical, would be a vertical, haven't really drawn it in, would be a vertical arrow passing through the nitrogen. In other words, all these individual NH dipoles are pointing upward. Their net combined effect would be directly upward, vertical, upward. And now there's two components that remain, the lone pair dipole moment and the resultant NH dipole moment. They're along the same line, they're both directed up. The net effect would be the summation of those, and the sum of those is this longer red dipole moment arrow. That's, as we figure out, the net dipole moment of ammonia. So indeed we figure out that the dipole moment of ammonia is greater than zero. It's a polar molecule.